Hi, and welcome back to Covidenomics. This is the first video in the second lecture. In this second set of videos, we're going to do a number of things. First, we're going to look at some epidemiological modelling, the standard susceptible, infected, recovered model, and show why exponential growth only applies at the beginning of a pandemic. Then we're going to go on and look at some examples of the SIR modelling, what it actually looks like with some numbers applied, and in particular we're going to show how test and trace can be really useful. Finally, we're going to have a look at some of the limitations of that modelling. In particular, we're going to come back to the economics, this is an economics course, and we're going to think about human reactions and what that means for the progress of a virus. Okay, let's think about this model. It's called SIR modelling because of the initials S for the people who are susceptible. That's going to be this ST here, the people who have not yet been infected in period T but are susceptible to infection. SI, because this IT here is going to stand for the people who are infected in period T and can pass on that infection. And R stands for recovered here. Sorry about R meaning a couple of different things depending on the different models you use. Here, capital R will stand for recovered. It's the people who have recovered or died in period T from the virus. And we're going to assume they can't be reinfected. We'll come back to that. So the total population, which is just given by N, can be divided into these three groups. Either an individual is susceptible to infection, they are infectious and can pass it on, or they have recovered from the infection or died and are no longer susceptible, and also they are no longer infectious, they can't pass it on. And we'll pop an initial reproduction rate on here given by beta. Now, why the change in notation? Well, because R now stands for recovered. Remember, beta, or the initial reproduction rate, is simply the chance you bump into somebody, so E, times the probability that person becomes infected, P. So that was done in the last video. And then we'll have a constant recovery rate, which will be given by gamma. So let's see how this little model works. If we want to know the number of infected people next period, well, we start off with the number of infected people this period. Some of those infected people will get better or die, and so they won't be infectious next period. What percentage is that? Well, we know it's the fraction here, gamma. So gamma is the recovery rate. So we know that gamma times IT are the number of people who are infected this period who will not be infected next period. So next period's infection is this period's number of infected minus those who will no longer be infectious next period. And then we've got this middle bit. These are the new infected people. Let's think about this term, beta times ST on N. What's that referring to? Well, remember, beta is this reproduction number. This reproduction number is made up of two things. Beta is simply this E, this exposure rate. So that's the number of people on average from the population that an infected person bumps into in one period, times P. And P is just the probability of infecting one of those exposed people. So person infected at time T will bump into a number of people and infect each of those people with probability P. But remember now, not all of our random people in the population can be infected. Some of them have recovered already. So what we actually need to think about is the probability that you bump into someone, E, times the probability that that person is able to be infected, which is simply the fraction of our population who are susceptible. So it's a fraction of a population who have not either got the infection now, and you can't infect someone who's already infected, or who has recovered and they can't get infected again. That's one of our assumptions, cannot be reinfected. So the likelihood of you infecting someone, if you're infectious today, is going to be beta, the number of people you'd bump into, times the probability that you infect one of those people, times the fraction of a population that is susceptible to the disease. Just to see how this works, let's do a simple example. Let's say that there are 100 people in the population. And let's say that beta equals 2. So on average, an infected person, say, bumps into 4 people, E is 4, and has a 50% chance of infecting one of those people. So E times P, 4 times a half is equal to 2. That's our initial reproduction rate. But out of our population, let's say that half of them are already either infected or recovered. So that the fraction here of people who are susceptible is only 50%. Well, in that situation, you bump into someone, there's a half chance that you can't infect them. And if you bump into them and they are susceptible, there's a half chance that you will infect them. So of those 4 people that you bump into, on average, 2 of them aren't susceptible. Of the other 2, 50% chance. So now you've reduced down that effective infection rate, effective reproduction number, to only 1. Now, that's for each infectious person, so we then just have to multiply by the number of infectious people to get the number of people infected in the next period by those who are currently infectious. So the number of people who are going to be infected next period on average is the number of people who are infected this period plus the number of people who are infected by the infected people this period minus the number of infected people this period who recover. So we can write the change in the number of infected people in period t plus 1 compared to period t. So it plus 1 minus it is simply given by this part here, this formula. So let's just move the formula up here and we can simplify it. Delta I, we can pull the it out from these two terms. So it's the number infected at time t times beta. Now what we've done here is we've noted that the number of susceptible people at time t is simply the total population minus the number of infected people at time t minus the number of recovered people at time t. And that gamma just comes from here. So with a bit of rearranging, we get this equation here. The number of new infections, the increase in new infections over time, depends on the number of existing infections times a constant. Well, that's just our exponential growth. But now we've got this bit over here. What's this bit over here? Well, this is the part that pulls down the rate of increase in new infections, depending on the number of people that have recovered or who are infectious as a proportion of the population. Notice a couple of things to start off with. Suppose that we had n infinite. We had an infinitely large population. Well, the n's down here, that term would disappear. So we would just simply end up in that situation with our exponential growth part of the equation. Or in other words, when we have a very large population and the epidemic's just starting, then essentially there's an infinite population from the point of view of the people that can be infected, and we have something that looks very much like exponential growth at those early stages of an infection, of a pandemic. But as the pandemic progresses and more people have recovered and are no longer able to be infected, that pulls down the increase in the new infections. So what we end up with is not an exponential growth curve, but we end up with an S-shaped or logistic curve. It's going to be a rate of growth of infections that initially rises exponentially, then starts to straighten up, and then starts to flatten off. This has implications for the course of a pandemic. Eventually the pandemic will burn itself out. That's essentially what this term is telling us. But when will it burn itself out? Well, to understand that, we need to think about the concept of herd immunity. When are there enough people in the population such that the rate of growth in infections actually starts to go down? when are more people recovering than are becoming infected. Once that starts to occur, then we're going to be in a situation where the pandemic, the rate of increase in new infections is going to be negative. So to work out how much of the population needs to either be infected or recovered to start reducing the rate of infections, what we call herd immunity threshold, we need to be slightly more precise. And we're going to do that by firstly defining really what we mean by this period of time t. It's been a bit vague so far, but we're going to define a period of time as essentially the length of time that it takes for a person to either recover or to die. Now, what does that mean? That means that this gamma here, well, it's now going to be nice and easy to write that. It's just going to be gamma is going to be equal to 1 by definition of the period of time. We're now going to be able to be a bit more precise about our initial reproduction rate. Our initial reproduction rate, previously we just said, well, it's the number of people you bump into per period times the probability of infecting. But really now what we're talking about is beta here being the number of people an infected person bumps into before they recover or die times the probability that when they bump into somebody that they infect them. The second bit which we're going to change here is we're going to pop across and look at this fraction here. That fraction there is just the fraction of the population who are not able to catch the disease, the fraction of a population who are not susceptible. So let's just simply refer to that. We're going to call that by the symbol alpha. We can now define the herd immunity threshold, HIT for short. It's going to be the fraction of the population, in other words, this alpha, so that the number of new infections, delta I, over here, so it no longer increases. So the herd immunity threshold is going to be the value of alpha that satisfies this equation that we've got given here. What is this equation? Well, it's simply delta I is equal to 0. To get that equal to 0, well, the number of infections isn't going to be equal to 0, so the IT comes out. It's got to be the rest of it that equals 0, and so that's going to be the situation where beta minus 1, which is now our gamma, and this all just becomes beta alpha. And that's what's down here. And reorganising, we get this simple formula here. So the herd immunity threshold is reached at a fraction of the population that have become immune to the virus, given by this formula, 1 minus 1 over this initial reproduction rate. So let's look at a few examples. Flu, the influenza virus. It's not particularly infectious in the sense that the initial reproduction rate or initial reproduction number is only about 1.5. So the herd immunity threshold is reached when 33% of the population are no longer susceptible to the disease. A couple of things though about influenza. First is, this explains why you should be taking your flu shot each year. While the flu vaccination is not perfect, it's based on last year's virus, not necessarily the current one. It helps create herd immunity and helps prevent flu spreading through the population. The other one is that flus differ significantly in their infectiousness and also in the death rate. So for example, in 1957 and 1958, there was what's sometimes called the Asian flu epidemic. It spread initially from first reported cases in Singapore in February 1957. It spread worldwide and killed about 1.1 million people. In contrast, if we look at measles, it is really infectious. The initial infection rate is about 18. So in other words, basically you bump into about 20 people that could become infected, and there's about a 90% chance of you infecting any one of them. So whilst you've got measles, so you transfer it on to about 18 other people. So its herd immunity threshold is really high. Now, of course, we have a vaccine against measles. Although we've got a vaccine, not everyone gets inoculated, either for themselves or for their children. But measles is deadly. Measles epidemics were common before there was a vaccine, and even since there's been a vaccine. Lots of people every year die from measles. So in 2017, about 110,000 people worldwide died from measles. In 2018, the number was about 140,000. Get the idea of a pattern here. In 2019, there was actually an epidemic of measles. A lot of this was driven by people refusing for themselves or their children to be vaccinated, so-called anti-vaxxers, who have conspiracy theories about the vaccine that have no scientific evidence. We haven't seen the death rate from 2019 yet. It's going to be higher. And finally, what about our current pandemic, COVID-19? Well, the initial reproduction rate, we're not sure what it is. Could be anywhere between 1.4 up to 4. So that means that the herd immunity threshold could be anywhere between about 30% of the population or 75% of the population. That is a big gap. It means that if we just let the pandemic run, we really have absolutely no idea how many people need to be infected and to have recovered before the virus will die out. And we're not sure of the death rate, so we're not sure how many million people will die if we let it run. That suggests there may be a bit of a role for government policy in here. Now, this video has been a fair bit of mathematics. In the next video, we'll ditch the maths and we'll look at some graphs that show the that S-shape rate for new infections using the SIR model with a virus such as COVID-19. We're then going to start thinking about people's reactions. And that might seem a bit odd. Why do we start with people's reactions? Well, because we're going to look at one of the weaknesses of this SIR model, and it really is straight back to the economics. In economics, we don't take people as randomly bumping into other people. People make decisions. We're going to see how those decisions can impact the rate of infection of a pandemic. Talk later.